regressive, classic moving average process. So the residuals in this case mirror the process itself because our prediction is so bad. Predicted value is so bad. We can also run that formal test of white noisedness. There's a new term for it. And it's pretty easy. It is literally what that stands for is WN white noise test, and it's the Q statistic. Remember, the null hypothesis is that the residuals are white noise. The null hypothesis is that there is no underlying cycle that's screwing up our prediction. Well, we know that prediction is bad. We get this Q statistic of 110. What does that mean? I don't know, but its p-value is 0. So in essence, whenever we get a p-value of 0, we reject the null that the residuals are white noise and conclude that we got a problem that we need to model. All right, how do we model this? Oh, we can also use this. It's kind of I like this one. These are 95% confidence intervals. If the residuals fall in here, it means that we have white noise. In this case, we can see that they're clearly falling outside of those 95% confidence intervals. And we don't have a white noise process. This is called a periodogram white noise test. All right, leaving those values in the table. All right, so let's estimate it. So we're no longer going to use red, we're going to use ARMA. And the way it works is that, let's ignore the I for now, but we specify in this the order of the AR process, the first letter, the first number, and then the order of the moving average process, which is the second one. This integrated thing we'll get to later. So, let's run it again. Essentially what it does, and we can get close to this with OLS, but we won't get the exact same results because this is estimated using an iterative process as opposed to our ordinary least squares regression optimization process. So what does it mean? A likelihood function is different than ordinary least squares, which is literally a mathematical formula that you use to calculate those, calculate your betas. An iterative process works a little bit differently. It finds the coefficients that maximize the likelihood that they would have come from that data. So they're trying different coefficients, and they're saying, does this look like it came from that data set? Let's try these ones. Does this look like it came from that data set? And then it finds the one that maximizes the likelihood that these coefficients represent the underlying data. Hence, it's an iterative process. It's going to try different ones. Notice it converged pretty quick after 8 iterations, but sometimes it's going to take longer. Sometimes it won't even converge. And essentially, what it does is we're actually not maximizing the likelihood, but we're maximizing the log of the likelihood function. But we're trying to maximize that likelihood function, so in this case it's negative, so the less negative the better. And you can see that each iteration should get smaller. So the first one is negative 215, the next one is negative 214, 0.2414, the next one's smaller with negative 214, 0.17, and then the other one is a little bit smaller, then it's 1.6, then it's 1.69, 164, then 1692, and so on. So it's trying to find the likelihood function that map throughput. That's the greatest, that's the biggest. Still have the same interpretation. Here's our constant. And then we have our ARMA process. So here's the moving average component. We specified, again, that. So essentially what this model is, so we looked at the autocorrelation coefficients, we looked at the partial autocorrelation coefficients. We determined it was a moving average process of order 1. So in essence, what we did is sales equals beta 0 plus beta, actually there's beta 0 plus, I guess, beta 1, plus, beta 1, our error term, ET minus 1, plus our error term there. So this is our moving average component, lagged error term. Again, it doesn't pick up very rich dynamics, but we'll see if it's better than our OLS. And we know how bad the OLS is. Sigma is an estimate of the variance of the error term. So we're going to want to, we're probably not going to deal with that too much. Let's see how bad our prediction is. Any questions? By the way, did I mention that this is usually taught like a full semester's ARMA processes? It's not. Especially the notation just kills you. All right, so we're going to predict, I called it HAT1 moving average, and then the residuals from the moving average process. So let's see what our moving average, our ARMA model looks like. It's actually just a moving average model. But better? Yeah. This is it. Remember, we've got no independent variables here. Why do we have no independent variables? Because we don't know what's causing this underlying cyclicality. It's just out there. We know it's there. We can see it. But there's no variable we can throw in there to model it. So what are we going to do? We're going to treat it as a moving average process, and the way we model it in this case is by just adding a lagged error term to the model. And that really did improve our regression results, our prediction results. Any questions? This is kind of mind-blowing, isn't it? We saw what the ordinary least squares regression did, and it was horrible. It was a straight line. It did nothing. Provided us no value at all. We're able to model this process completely unknowing anything about it. We don't know what's causing it. We have no idea what's causing it, but we're able to model it pretty decently. I mean, it's not that bad. It's not perfect, but it's not that bad. That's pretty cool. That's amazing. Let's look at the residuals. Are we able to eliminate the pattern in the residuals? So let's look at the residuals. And we'll look at the residuals at this. It says right here, look at the residuals. We'll check the residuals. So here's a graph of the residuals. Do we see a pattern? I put the OLS residuals in blue and the moving average residuals in red. Again, you can see much more persistence in the OLS residuals. It's hard to tell. I mean, it's kind of visually, it's hard to tell if we've eliminated the serial correlation. So we'll just do it, look at the autocorrelation coefficients, partial autocorrelation coefficients, and we'll look at the Q statistic. Nice. Nothing significant. Again, meaning we've pretty much cleaned up, we've white noisified those residuals. Let's run the box statistic, box Q statistic. These are errors from our moving average model. Remember, the null hypothesis is that we have white noise. And the alternative hypothesis is that we still have some serial correlation in there. We've got a p-value of 0.3, we're not going to reject that. So we're going to fail to reject the null hypothesis and conclude that we've successfully eliminated any serial correlation in our error terms. We've improved our model, and hence we're going to improve our forecast. All of this stupid little thing. This is pretty cool. It's impressive. It's impressive. Any questions? I'll pat myself on the back. It's not like I invented this either. This is like I said, if you take a forecasting class, and a lot of universities will offer a class just in forecasting, this is what you're going to do all semester. Is this stuff. All right. So again, this was pretty easy because it was a pure moving average process. Let's try to make it tougher for us to identify and then model the process. But again, no questions? Are we following? All right, let's try another one. This is an MA2 process. So again, I'm going to artificially make it so that I know exactly what it is. Then, since we know this is truly a moving average process with theta of 0.9, theta 1 of 0.9, and theta 2 of -1, we want to see if our tools available to us can help us properly identify it. So we don't need to know the thetas, but we do need to know the order of the process. So we're going to pretend that we don't know what's going on here. We've just got this time series on sales. All right, there it is. Again, we don't know, ignore the moving average 2 process, we don't know that. We're going to look at the autocorrelation and partial autocorrelation coefficients. This is going to give us a clue. Remember abrupt cutoff after the first one. We're not really capturing the second order nature of the moving average process. So we probably look at an MA1 process, or model this as an MA1 process. So let's see if we have any other clues. All right, let's go back to OLS. We know how bad that is. I shouldn't even do that. It's kind of good to see how bad things are. So we're just going to model it as using our ordinary least squares regression. Again, we get a horrible prediction. It's that red dashed line, which is ignoring all of the cyclicality in there. We look at the residuals, and we know those are going to be pretty bad. And let's just look at the. All right, we can do that. Let's just run the Q statistic on the test. Yeah. So again, p-value of 0, we're rejecting the null hypothesis, which is that the residuals are white noise, and concluding, okay, OLS just isn't working. We're getting a horrible prediction. We got serial correlation in the errors. We're violating a bunch of stuff. All right, so let's run this as I'm going to run this as an AR1 process. I'm sorry, yeah. Moving average 1 process first because we're kind of cheating here because it looked to me like an AR1 process. So, and then I'm going to see if we can improve our forecast. And then I'm going to do this. So this is the proper one. We know it's a AR2 process, so let's just add 2 there. 2 there. All right, let's look at our results. First one, we know it's an MA2 process, but we erroneously model it as an MA1 process. Let's see how well that prediction comes out. How those predictions come out. And we can test the residuals. It doesn't look that bad. I mean, it doesn't look that bad. Again, this should be MA1. But let's see if we can't. Let's look at the residuals and see if we eliminated the serial correlation and the errors. Let's just go keep this. We've still got some serial correlation in there. So remember, the null hypothesis is that the residuals are white noise. We're 10%, we're not rejecting that 10%. So we're close. We're borderline, right? So I mean, I've never heard of a 12% level of significance, but this is pretty close to 10%. So it's not like we're real comfortable with this. Let's look at our prediction using a true the true AR2 process. And what did I do? Did I add the 2 there? Yes, I added the 2 there. I'm going to add the MA1 process in there also. I don't know, it's much different. Let's see. I'm not even going to put y hat in there. I'm going to put hat. Let's see how similar these are. So these are the 2 predicted values. They're pretty close, aren't they? Again, illustrating the fact that moving average processes in general capture relatively weak dynamics. So even if we mistakenly model this as an MA1 process, as opposed to an MA2 process, which it actually is, I don't think we'd be making too big of a mistake. We were pretty close. I don't know what the correlation, well, we can't look at the correlation between those two, but they're pretty close. That's not necessarily going to be true of autoregressive processes, which we know can differ fast. Let's see, regress, there's must be a correlation between these two. That. Yeah. Look at our R squared. Yeah. And our coefficient is almost 1 also. So moving average processes, again, in general, are they don't differ too much from each other. but we saw that earlier. So we wouldn't be making too big of a mistake if we, again, use the MA1 process instead of the MA2 process. Although we should check the residuals and see if we're able to fix that. So where is my... So let's change this to MA2. And at least see if we can be a little bit more secure in our failing to reject. Barely. So what do we have, 11% before? Now we got 16%. So we said 11 was pretty close to, or 12 was pretty close to 10. 16 is you're getting kind of further away from 10. So is it that big of a difference? Yeah, I mean 10%. You know, we're pretty close to that 10% level, but here I think we're far enough to be a little bit more confident in our results. Does that make sense? Because again, in reality, we're not going to know the true order of these processes. Unlike these, where I literally baked the data myself. All right, let's do a moving average process. Yeah.
I thought it was an indicator that we did something wrong if we got adjusted R squared of 1. I remember that from last semester.
Yeah. We should never get an R squared of 1.
It's just a bit possible.
Which means these are kind of in practice. We should never get an R squared of 1. Remember what we're doing. We're not really modeling something. We're just trying to see, are these two processes the same? And it turns out pretty close to being exactly the same. But yeah, you're right. You never want to get an R squared of 1. That means screw something up. All right. Let's look at an autoregressive process. Okay. So again, I'm going to construct two processes, two AR processes, one of V of 0.9, one of... So we already saw these. But now we see the difference in the values, the difference that the values make of our autoregressive coefficient, D. And again, much richer dynamics, much richer persistence versus the phi of 0.4. Let's see if we can model these. We could again try ordinary least squares. We can do that again. Similarly bad results. What do we model? We're modeling this is the first one. I think this is phi of 0.9. So again, why aren't we capturing any of that cyclicality? Because we don't know what's causing it. We have no way of modeling it. Pretty prominent, pretty obvious. We're going to get some serious serial correlation in our error terms, because again, serial correlation just means there's a predictable nature to our errors. When we overpredict, we tend to overpredict. When we underpredict, we tend to, actually when we underpredict, we tend to underpredict. When we overpredict, we tend to overpredict. And we're following this same cycle in our residuals. So these residuals should be a lot more obvious that there is serial correlation, that there's a problem with the residuals. Yeah, so again, we're seeing kind of the nature of the underlying cycle that we don't know what's causing. And again, we can look at the autocorrelation and partial autocorrelation coefficients of our residuals. And again, classic autoregressive process. geometric decay. And then it looks like we've got oscillating decay, but abrupt after the first one. All right, so let's model this as, and we know we're going to fail. I'm sorry, yeah, we know we're going to reject white noise test. But in case you don't believe me, in case you think it's fake news, let's do it anyways. So we're clearly rejecting the null hypothesis, which is that the residuals are truly white noise, perfectly linear. Not even close. All right, so let's model this as an ARMA process, or more precisely, an autoregressive process. So again, AR is the first component, and the MA is the last component. So literally what we're running now is beta 0 plus beta 1 sales t minus 1 plus our error term. So that's what we're doing when we're running an autoregressive of order 1. We're calling this phi though, right? These are called phis. We know that the true value, remember we constructed this data set, the true value of phi, the autoregressive component, is 0.9, and we're getting a pretty close estimate of that, of 0.9. So our autoregressive process is capturing the underlying cyclicality of the data. Let's see what our prediction looks like. Ideally, we can improve that. So there's still some serial correlation. We're going to check the residuals, but there still appears to be some serial correlation in there. In other words, here we're over-predicting, and we're over-predicting on a pretty consistent basis. Here we're under-predicting, and we're under-predicting on a pretty consistent basis. What you want for true white noise is you don't want a pattern to your error term. So if this is the true data, this is sales, our predicted shouldn't be consistently doing that, and then consistently doing that, and then consistently doing that. What you want is for it to be kind of hovering back and forth on that line, right? That's kind of the true white noise error term. Now, this looks like there's still some serial correlation, but we won't know until we actually test it. It's clearly better than ordinary least squares regression, which is missing all of that underlying cyclicality. And again, important to distinguish cyclicality from seasonality. We know how to model seasonality. We can throw in monthly dummies or quarterly dummies or whatever it is we need to do that. So let's look at the residuals. All right, so the OLS residuals are in the blue. Those are horrible. And the, that should be AR. That should be AR1 process, not MA2. Let's make sure I got that right. Yeah, it should be AR. So that's a mistake. Too much copying and pasting. Along with too much wine.
Never too much.
Usually a good combo. But every now and again you get that. So clearly our residuals were not white noise. I still see a pattern in there, right? I can still see kind of a pattern here. But we'll know when we test it. So here it's pretty close. So let's look at the autocorrelation coefficient and the partial autocorrelation coefficient of the residuals. Okay, whether or not there's a pattern, what do we know about it? It's not statistically significant. So according to our autocorrelation coefficients and partial autocorrelation coefficients, we've effectively eliminated any pattern in our residuals. So our residuals appear to be true white noise. Now we'll run the Lejeune box Q statistic, but based on the auto and partial autocorrelation coefficients, it looks like we did our job. Eliminated serial correlation, improved our forecast, improved our model. Let's run our test, our white noise test. And cross our fingers. Yes. We're pretty confident. So a p-value of 0.8, what we're looking at is something close to 0. P-value only goes with the probability, so it's 0 to 1. So we're pretty confident that we've eliminated any serial correlation from our error terms. We've improved our model, which is going to improve our forecast. So autoregressive models are going to capture much richer dynamics than moving average processes. Any questions? Pretty cool stuff? Yeah. All right. Let's see. Oh, we want to see something cool. You're not going to have to do this one. This has to do with checking whether or not the roots are real or imaginary and whether they lie inside that unit circle. So this is all the stuff we skip. It's kind of cool.
It's not going to mysteriously appear on the homework, right?
Be prepared.
Good.
Problem 4. What do the Boy Scouts say?
Yeah.
Always be prepared.
Let's see, OLS2, this is the second one. Let's do a, this is the second one. Here's an AR2 process. All right, so this is an autoregressive 2 process, of order 2, that's the terminology. Let's see what it looks like. Yeah, it's not that obvious in there. It's not as obvious as the autoregressive of order 1 with phi of 0.9. Now we've got